As we journey from the vast reaches of the Milky Way down to Earth, we are reminded of the beauty and fragility of our planet. Yet, beneath this beauty lies an ongoing challenge: pollution from human activity threatening ecosystems and health. This is where bioremediation steps in, harnessing the power of microorganisms to break down toxic pollutants, naturally restoring balance to our environment. From oil spills to industrial waste, bioremediation offers a sustainable solution for cleaning up our world. Hello everyone, my name is Samriddhi and today I'll be presenting on the topic Factors Affecting Bioremediation Part 2.
So, what is bioremediation? Bioremediation is a natural and sustainable process used by microorganisms like fungi and bacteria. So, this tiny cleanup crew of nature will go and break down all the toxic chemicals present in our environment and make them turn into a very harmless substance. By bioremediation, we can clean up soil, air and water and make them habitable for all the organisms present in environment. Bioremediation can be divided into two broad categories. One is in situ bioremediation and ex situ bioremediation. In situ bioremediation is a process where the contaminated soil is treated on the site itself. Here we are going to stimulate the native microbes to degrade the pollutants. This one is very cost effective and it will be effective in a large scale contamination site. But other hand, for ex situ bioremediation, we have to take the contaminated soil and water and treat it elsewhere. So there it will be more controlled environment, but again it will be very costly and also it will be logistically very difficult. Now let's talk about factors affecting bioremediation. Here I will only talk about environmental factors, physical factors and site-specific factors. So let's get started. Environmental factors that will affect the bioremediation process are pH, temperature, the moisture content and oxygen availability. So first comes temperature. Temperature plays a critical role in influencing the enzyme activity and metabolic roles in bioremediation process. So many organisms, actually most of the organisms likes to stay in the optimal temperature of 15 degree to 35 degrees C. But when the lower temperature or higher temperature comes, the enzyme activity will respectively slow down or will completely stop. So for that areas where contamination happens in very colder regions like Alaska or very hotter regions like Sahara Desert, there we can use extremophilic organisms like saprophiles or thermophilic organisms for breakdowning those contaminants. pH will affect the microbial growth and also their enzymatic activities. So most neutral pH is like 6 to 7 is habitable for most of the microorganisms, but most of the bioremediated microorganisms can be slightly acidic or alkaline in nature. They like those kind of environments. But if it's more in amount, if the environment is more acidic or more alkaline, their enzymatic activity will stop. So for those areas again we are not going to use many extremophilic microorganisms. Like for acid rain, when the acid from the acid mines, the acid rain will come where all the acidic products will come out and mix on the landfills. There acidic or acidophilic microorganisms can be used. Next is oxygen availability. Oxygen level decides that the process the microbes will go through will be aerobic or anaerobic in nature. If the site is aerobic, like the contaminants are organic in nature, then for breaking down hydrocarbons, we'll be needing aerobic microorganisms, and for breaking down heavy metals or those kind of contaminants will be needing anaerobic microorganisms. So oxygen level will decide if the microorganisms present in the environment will break down some specific type of pollutants. If not, then all of the microorganisms will start acting all together, and at the end nothing will be there. In the bioremediation process of oil spill, scientists often go and inject the oxygen from outside to speed up the contaminant degradation process. Last one is moisture content. Adequate moisture availability is very important in bioremediation process. If moisture is not in a normal balanced condition, then if it's more, it will become anaerobic condition for the microorganisms, and if it's very less, microbial movement or mobility will be disrupted. So that's why in drought prone areas, the moisture level should be in balance for the microorganism to start the bioremediation process. Next one is physical factors, and these factors are soil structure and porosity, contaminant bioavailability, particle size, and hydrophobicity of contaminants. First is soil structure and porosity. Highly porous soil will make the movement of water, nutrients and microbes easier in the area. But for soil with less porosity, the contaminants will be present in one area, but the movement of microbes will stop or halt. So in these cases, sand soils and clay soils we can take. In sandy soils, the water, nutrients and also microbes will move freely. But also the contaminants can leach through and go to deeper areas. That is also a bad thing. But in clay, more non-porous soil, the contaminants can stay in one place, but the microorganism will not be able to move freely. So that will also make the bioremediation process slow. So for proper bioremediation, we need a balanced soil structure and porosity to make the movement of nutrients, water and also microbes in a very balanced speed. Next one is contaminant bioavailability. Here bioavailability refers to the fact how much the microbes can go and degrade, and how much they are available for the microorganism to degrade. So here what will happen if the contaminants are hydrophobic in nature, suppose oil, then they will go and bind or adsorb in soil particles. So it will be less available for the microorganisms. In that process, we can add some surfactants to or emulsifier to make those elements like oils more available to the microorganisms. Then will come particle size. The size of soil particles will define how bacteria or other microorganisms can go and bind to the pollutants. If it's a clay kind of soil, then the surface area will be more. So more microbes can go and bind to them. But then again, if clay particles will be so non-porous, the movements of microbes will halt. But again for sands, the surface area will be lesser, but again the movements will be more sufficient for the microbes to remediate all the pollutants. So in this case again we need more balance of soil particles to make the bioremediation process easier. And the last one is chemical nature of contaminants, or you can say hydrophobicity of contaminants. Here the chemical nature, mostly the hydrophobicity, will influence the remediation process more, because if the pollutants are not soluble to water, microbes won't be able to properly digest them and remediate those pollutants. So here we can use again those emulsifiers and surfactants to make the oils or those hydrophobic elements more available to microorganisms. And then comes site-specific factors, and these are contaminant concentration and distribution, presence of co-contaminants, site geology and hydrology, nutrient availability and organic matter content, and at the end its previous site, treatment or pollution history. First one is contaminant concentration and distribution. If in some places the contaminants are in dispersed nature, then scientists often favor the in situ bioremediation. And for those places where there are too much contaminants present, or we can call them hotspots, there scientists prefer to do ex situ bioremediation, because if the contaminants are too high in nature, it will become toxic to the microorganisms, and or again if it's too less in nature, then it will become the biodegradation process will slow down innately, because the unavailability of nutrients, because those microorganisms will break down those pollutants to get nutrients, right? If there is lesser amount of pollutants, so they won't get proper nutrients, so the degradation process will also slow down. Okay. Next one is presence of co-contaminants. The amount and variety of contaminants present in a place can impact on the bioremediation process in general. So if there is heavy metals and or organic compounds present in a diversity in nature, then what will happen? They will interact with each other and organisms. If some microorganisms are aerobic in nature, they won't be able to degrade the heavy metals, and they can also be toxic for the microorganisms. So in that process, the organic compounds won't be degraded because the microorganism can't live in those nature. So here, for proper, if the area, the main contaminant is organic in nature, then we need bioengineered strains or specific strains that will be mental toxicity tolerant in those areas. Next one is site geology and hydrology. The soil type, the groundwater flow, all of these can affect the bioremediation process. If the groundwater flow is more in some area, contaminants can flow to other area. If that particular area is their treatment is done, then the contaminant will flow and go to another area where the specific engineered strains that scientists put is not there. So the contamination will be moving around. Okay, so that will cause impact in bioremediation process. Also soil type, like I previously said, if the soil is more permeable, the contaminants will leach through and go to the more deeper part of soils. And if the soil type is more clay-like, then the movement will completely halt, and again the soil remediation process will slow down. Next comes nutrient availability and organic matter content. So if a area is nutrient poor in nature, then most microorganisms won't be able to live or sustain their life in those soil. But if the area is way too organic matter rich, then also competition between many other microorganisms will come, and our desired microorganism may be not that like powerful for them, and they may be die. So we need a balanced area for them to sustain their life there. And in many cases, if the area is polluted by hydrocarbon rich pollutants, then scientists use artificially added nitrogen or phosphorus to make the soil more nutrient rich in nature, so that the microorganisms can sustain their life. And the last one is previous site treatment and pollution history. So if in one site previously same kind of contamination had happened, then the microbial community present in those areas is already they already have those ability to degrade those contaminant or pollutants. So, but there is a catch. If those area was treated with chemicals for treatment, then maybe those microorganisms are already dying, and the availability of microorganisms will be way less. In those cases, we have to use biostimulation, and we have to add more nutrients to the soil to make the microorganisms present in those areas more active, and the availability of those microorganisms will enrich. By that we can degrade and those pollutants more effectively. Like if the area is polluted with hydrocarbons, then maybe those microorganisms already have those ability, and they have modified their pathways to degrade those particular hydrocarbons. By those and by that like by those methods we can always do the bioremediation process. So these were all the factors that are used and that are studied more like effectively to remediate all the pollutants and contaminants present in our environment.
Now let us go through some real life studies done on bioremediation. In Assam, India, a petroleum hydrocarbon contaminated site provided the basis for a bioremediation study using a hydrocarbon degrading strain identified as Serratia. This strain reduced surface tension in petroleum oil media by 48.35% within 7 days and exhibited chemotaxis toward hydrocarbons. It achieved significant degradation rates of 87.54% for diesel and 85.48% for kerosene over 28 days. In an ex situ pilot scale bioremediation experiment, soil contaminated with 10% and 20% kerosene supported germination rates of Vigna radiata seeds at 52% and 72% respectively within 7 days. Plantlets in these treated conditions exhibited greater heights compared to control in untreated soil, showcasing the potential for restoring plant growth in contaminated environments. Even heavily polluted soil samples yielded a 31% germination rate after 20 days of bioremediation treatment. Biosurfactants produced by Serratia, confirmed via FTIR analysis, played a key role in emulsifying and breaking down hydrocarbons. This study highlights the potential of Serratia-based bioremediation as an eco-friendly approach for rehabilitating petroleum-contaminated soils. The Exxon Valdez oil spill of 1989 was one of the worst environmental disasters in history, spilling 11 million gallons of crude oil into Alaska's Prince William Sound. It devastated ecosystems, killing hundreds of thousands of animals, including seabirds, sea otters, and orcas, and contaminating over 1,300 miles of coastline. The spill crippled local fisheries, disrupted livelihoods, and left long-lasting ecological scars. Bioremediation played a key role in cleanup efforts. Scientists added nitrogen and phosphorus fertilizers to stimulate native oil-degrading microbes. This bacteria broke down hydrocarbons into less harmful compounds, speeding up natural recovery. Despite these efforts, the consequences were profound. Buried oil remains in sediments, and some species like Pacific herring are still struggling to recover decades later. This tragedy led us to the US Oil Pollution Act of 1990, improving tanker safety and spill prevention. The Exxon Valdez remains a stark reminder of the catastrophic risks associated with oil transportation and the vital role of science in mitigating environmental disasters. Thank you everyone for listening to my presentation. I hope you all will be more respectful and cautious towards our nature. These are my references. Have a great day.